Hardware features can make the programming task easier and improve system efficiency. We show how some simple hardware instructions can be used to solve the critical section problem. All these solutions are based on the premise of locking, that is, protecting critical sections through the use of locks. As we shall see, the designs of such locks can be quite sophisticated. We start by presenting some simple hardware instructions that are available on many systems and showing how they can be used effectively in solving the critical section problem. Hardware features can make any programming task easier and improve system efficiency. Some machines support test and assign instruction. It tests and modifies the content of a word atomically. I emphasize this atomically because it is a machine instruction. So during its execution, it cannot be interrupted. But because it doesn't refer to any discrete CPU, so we just use the pseudocode to describe the function of the machine instruction. So you must know, though we describe it in high-level language statement, but actually this is the function of a machine instruction. Okay, so test and assign. Actually, it test and assign and the Boolean variable, and you can see first, the target is assigned to RV, then we assign target equal to true and then return the value of RV. So the important character is that this instruction is executed atomically. That is, it is one uninterruptible unit. So mutual exclusion with test and assign. This is critical. This is shared data log. Just now we say we will use this shared data log to log the critical section. Actually, it is unlog. So log equals to false. Okay. Then in process PI, we test and assign log. If it is equal false, then this machine instruction will cite log equals to true. That means log the critical section. After finish critical section, then we'll assign log false. That means unlock the critical section. So this satisfies mutual exclusion and also satisfy progress, but it doesn't satisfy bounded waiting requirement. Okay, and some machines support swap operation. It atomically swaps two variables. So we also use high-level language. Also, we say pseudocode to describe the machine instruction swap. Okay, it is a machine instruction. We just describe the function of this machine instruction. It swaps two Boolean variable A, B. Okay, and also we use a temporary variable temp. And it equals to A. We assign the value of A to temp. Then we assign the value B to A. Then we assign the value temp to B. That means exchange, swap the value of A and B. Okay, you must remember this function is executed uninterruptible. Okay, So mutual exclusion with swap. A global Boolean variable log initialized to false. Also, log is used for logging the critical section. So initially it equals to false. That means the critical section is unlocked. Okay. So each process also has a local Boolean variable key. At first, key equal to true. That means process PJ want to enter its critical section, and we swap log and the key. So you can see if log equals to false, then the while condition will pass. Okay, so if log equals to true, that means the critical section is locked. Another process is executing its critical section. Then the process PI has to wait. Okay, so only the log equals to false, then process PI can execute its critical section. After finishing, it will assign log false. That means unlock the critical section. Okay, so this solution doesn't satisfy bounded waiting requirement because after leave the critical section, the process assign the log false, then it can enter again and again. Okay, and other process cannot enter the critical section. Okay, so doesn't satisfy bounded waiting.